Okay, so today we're going over LeetCode 1631, path with minimum effort. This is of medium difficulty, and sure, yeah, we'll upvote it. You are a hiker preparing for an upcoming hike. You are given heights, a 2D array of size, row times columns, where heights, row column represents the height of cell, row column. You are situated in the top left, 0, 0, and you hope to travel to the bottom right. So 0, 0 to bottom right. Rows -1, columns -1. We're using zero-based indexing. You can move up, down, left, right, and you wish to find a route that requires the minimum effort. A route's effort is the maximum absolute difference in heights between two consecutive cells of the route. Return the minimum effort required to travel from the top left cell to the bottom right cell. This is something where we clearly use Dijkstra's because any pathfinding algorithm with non-negative weights is where you want to use Dijkstra's. And yeah, so this is just an easy go-to for Dijkstra's. We're going to go through example 1 here, and if we look at our heights map, um, we can see that 1, 3, 5, 3, 5 is going to have output 2. Basically, we never have to exert more than two minimum effort to go along this path. If we were to go from 1, 2, 2 to 5, we would have to exert an effort of 3. Along this final 2, 5. And so the maximum effort would be we would have to exert a effort of 3, which is greater than an effort of 2 along this route. Similarly, along example 2, 1, 2, 3, 4, 5, we never have to exert an effort greater than 1. But if we go 1, 3, 5, 3, 5, we have to exert an effort of 2 to go along this path. So yeah, the optimal minimum effort path is highlighted here. And then you can see here we're just going in this this kind of zigzag of ones, and that gives us an minimal effort of 0. Basically, we're just walking a level path here, and yeah, obviously we wouldn't want to go over these hills. You know, that wouldn't make sense because we would have to exert an effort of 1. So I basically wrote this Dijkstra's code, which uses a min heap, so that it would be readable. So number of rows, number of columns. That's yeah, the number of rows is how many arrays there are, and the length of the individual arrays. So it's a 3 by 3. The efforts. So if you look at my output here, basically we instantiate the entire efforts table to be all infinity, and then we mark our first starting position as 0 because it doesn't take any effort just to be where we are. And then going through example 1, we start with our current heap of 0, 0, 0, and that just means it takes 0 effort to be where we are, and our current position is 0, 0, our top left. And then our current efforts, this is our heights table, which is the same as this, and our yeah, and then so if we go from the next direction right, if we go right, that's going to take an effort of 1. We can see that here. It takes an effort of 1, so we fill that in. we update the efforts table and we push to the min heap 101, which basically is the effort to go from 0, 0 to 0, 1. And then our next direction, if we go left, that's going to push us out of bounds. So we don't even consider that. Next direction, down. So if we, okay, just a second here, sorry. Okay, let's keep going here. And basically, yeah, if just going through the algorithm again, we're popping off the minimum next effort, and we're considering right, left, down, up directions, and yeah, we're checking that we're not out of bounds for the next direction, and we're determining how much that next move costs, and if that next move is less than what we have recorded in our efforts table, then we mark down that as our next. We update our efforts table with the new minimum weight, and when we push that next effort with the next step onto the heap. So going from here, if we try next direction left, going from 0, 0, that next direction down, going from 0, 0, that takes 2 effort. We update our efforts table and we push that onto the min heap. We're gonna visit 1, 0 next with an effort of 2. Going up from 0, 0 is out of bounds. So iteration 2, we have our 101 and 210, and 101 goes to the first in line because it's a priority queue, it's a min heap. So this weight of 1, position 0, 1 with a weight of, with an effort of 1 is considered. Going right from 0, 1 would going right from 0, 1 takes 1 effort, so we update that here and we push that to the min heap. Going left from 0, 1, sorry, going down from 0, 1 takes an effort of 6, which is less than infinity, so we update the table. Also, when we consider going left, that makes us go backwards in pathfinding, and we're trying to find the minimum path. So going backwards just causes more work, so we don't want to go backwards. Direction up is out of bounds, so we don't want to go out of bounds here. Let's see. Iteration 3. So we look at our current heap, 102, 210. So this one with minimum effort floats up to the top of the min heap, and then we're considering our position 0, 2, and then that going right is out of bounds, so that doesn't work. Going left is going backwards, so that doesn't work. Going down has a weight of 1 effort, so we mark our efforts table accordingly. And then let's see here, and then we push that next position to the min heap. So it takes an effort of 1 and position 1, 2, and then going up from this position is out of bounds. Okay, iteration 4. So basically we have our position 1, 1, 2, which lands us right here. Going right from that is out of bounds. Going left from that is going backwards, because we've already explored this position, so we don't want to go backwards. And then going down from our position 1, 2, you can see 5 minus 2 is 3, so we update that and we push that to the min heap 3, 2, 2, and and then going up from here would be going backwards, because we've already been to this position. Okay. So 1, 0. So 1, 0 floats to the top of our next minimum effort. We do next direction right. 5 is less than 6, so going from 1 to 0 takes 5 effort, which is less than. I think we were going down from this position before. Yeah, so we were going from 2 to 8, but actually it's cheaper to go from 3 to 8. So we update our minimum effort table to 5, and then we push that to the min heap. So 1, 1, we push that to the min heap as accordingly. Going left from this position just pushes us out of bounds. Going down from this position takes 2 effort. 5 minus 3 is 2, so we update our table accordingly. Put a 2 here, and we push that also to the min heap. And next direction is up. That would make us go backwards, so that would put us just back to our start point, so we don't want to go backwards. Okay, iteration 6. So I'm sorry, go back here. Iteration 6. So the position 2, 0, row 2, column 0 floats to the top as the next lowest effort position to investigate. So if going right is less than infinity, which takes 2 effort, of course it is less effort, so we update our table accordingly, and we push that to the min heap of getting to 2, 1 takes 2 effort. Going left from this position would push us out of bounds. Going down from this position would push us out of bounds. Going up from this position would make us go backwards. So we go to iteration 7, and that is position 2, 2. I'm sorry, position 2, 1, and that we start from that position. Does going right from this position, is that less than what we'd last recorded? So yes, we tried to get to this position before from 2, 5. We went from 2 to 5, 2 to 5. That takes 3. But if going 3 to 5, that takes less effort too. So we update our minimum efforts table from 3 to 2, and then we push that to the min heap as another position to investigate. Going left from our current position, which is 2, 1. So 2, 1 is right here, and that would going left from that position would make us go backwards. Going down would push us out of bounds. Going up would make us go backwards. So that ends that iteration. And then position 2, 2. So this final position floats to the top, and we have reached the endpoint, the bottom right corner. So we have updated our final efforts table, and yeah, so we can see if we go along this path, this path that I'm highlighting here, um, yeah, that takes minimum effort too. Um, and so yeah, there we go. And when we're reading this efforts table, we're just looking at our endpoint, right? We don't look at this pathway that we took. We look at the endpoint, which is the bottom right corner, and that has been updated with the lowest amount of cost to get to that point, and that has shown to be 2, and that's 2 is our final answer. Okay, thanks guys.